Yeah, it's working now.
Can I start?
Yeah, it's a stream on YouTube now. You can start whenever you want.
Okay, so then, can you see these slides?
Yeah, you can see.
Yeah.
Okay, then, okay, so let's start. Hello everyone, I'm Jungwoo Park, the first author of this paper Monet, and today I'm gonna introduce my paper, our research and the results about this. So thanks to Jaewoo Lim, he invited me to this community and give a chance to introduce my paper, and also thanks to Jin Ahn. He actually his nickname is Snoop Two Hat. Also in this stream, so he made this presentation, this slide, and I modified this for today's presentation. So I already see some YouTube, some records in your YouTube channels, and I see that many people just read the paper directly without any other slides. So I think so. Although I prepared this presentation, but it would be better to move to this paper if we need it. So there are really many things that is not in this presentation slides. So I frequently move on this paper if you need it. So okay, so let's start. Our paper name title is Mixture of Monosemantic Experts for Transformers, and as you know, maybe you can guess, this is the combination of MOE, Mixture of Experts, and the monosemantic methods like sparse autoencoder. So, okay, so this is the title, and I summarize our paper's motivations and methods and results. So maybe I'm pretty sure that you guys are master of sparse autoencoder and many kind of this interpretability. So maybe I will skip the importance of monosemanticity and the interpretability. So in other perspective, I want to aim the limitation of sparse autoencoder like post-hoc training scheme. So I will explain detailedly after this slide, but maybe you understand that sparse autoencoder is should be trained after trained on the pre-trained model, so that we have to bring a new neural network to actually approximate and actually train to reconstruct the hidden vector hidden state of the LLMs, while adding the regularization and the constraint of the sparsity in the feature space, so that it is in practical. It is almost impossible to achieve the zero reconstruction error that requires the reconstruction error of the decoded hidden vector, and this has finally occurred the performance drop in LLMs. So I will say about this in the later slide. And in other perspective, we also aim the domain specialization in MOE. So some kind of OLMOE and other papers using fine-grained MOE, using more dividing the experts into sub-experts, like these methods, shows some kind of domain specialization like SAE, but they are actually using really small number of experts, so that this is not quite enough to see the monosemanticity in the MOE. So we thought that how about combining them into a single architecture? So as you know, the sparse autoencoder is usually showing the more fine-grained and more detailed features if we increase the number of features. This is some kind of, you can see in the entropic blows, and So more number of experts shows more detailed and more fine-grained clusters in the feature space embeddings. So that, how about just increasing the number of experts like SAE? So usually sparse autoencoder uses some about more than 10,000 and 100,000 number of features. So how about increasing the number of experts like SAE that scales? But actually, this is almost impossible in practice because this is really expensive and heavy, and memory footprints are really, the problem actually. So because of that, our paper, our method is actually to achieve increasing the number of experts. This is how we can achieve by using the decomposition methods to act, although the memory is not really heavy, but we can make the model to act like effective number of experts, like more than thousands or more than 100,000 scales for mixture of experts. So using this, like SAE, similar to SAE, we can also achieve some kind of monosemanticity. Like we actually cannot prove restrictly, but in qualitative results and some kind of other indirect experiment results, we think that this looks like our Monet, with many number of experts can achieve some kind of SAE's monosemanticity like. So using that, and of course our model learned the monosemanticity in end-to-end scheme, so our model can effectively manipulate by just pruning the specific experts without any other performance drop. So that is our point. So using the sparse autoencoder directly cannot be applied for the manipulation because of their reconstruction error. But if we train them in an end-to-end architecture, then we can the model can the model is already adapted to the reconstruction error when actually the distribution shift of the expert routing, so that we can control the model by just manipulating the expert's routing course. So this is a simple summary, so I will explain detailedly. I think so. This presentation is for other purpose, is created by other purpose. So I think this is fine to skip this part, the importance of interpretability. So there are many other interpretability methods like GradCam and the tension-based, and this is actually famous. This till.pub blog, and this is talking that inception as early layers neuron shows some kind of semantic neurons they have. So, but in case of transformer, we cannot directly use the neurons in the hidden vectors, so that the sparse autoencoder is created to expand the feature space to more than original hidden dimensionality with the sparsity constraint. So it can be applied to closed sonnet, and you can see the related features like these visualizations, and also in multimodal schemes. So, but in our paper, we want to aim the limitations of the sparse autoencoder. But I want to say that our paper is not just saying that do not use sparse autoencoder, but just use our model. This is not our point, but these limitations are some kind of fundamental and theoretical thing. Because of that, also there should be some other useful practical alternative methods, but we are talking about really trivial and fundamental kind of things. So the first one is this is all about postdoc separated trainings problem. So first one is it should be, and it might be happen. The feature space mismatch misalignment can be happened because sparse autoencoder should be trained after the pre-training the LLM. So we need to prepare the corpus for SAE. But let's think about Gemma or Llama. We do not know the actual pre-training corpus of the LLMs. So we actually use some general alternative corpus, some kind of C4 or red pajama or other things. But this is theoretically not correctly same as the LLM's corpus, so that there should be some ignored features, maybe ignored. So let's think about a really simple case. So if we train SAE on a mass corpus, then maybe we cannot see. Maybe we can only see the mass-related features, but other general features cannot be captured. So because of that, this is separate. This is because of separated training pipeline, so that the corpus mismatch can be happened. Anyway, so the second one is non-zero irreducible loss. So as I mentioned before, the sparse autoencoder is another neural network to encode to the sparse feature space and then decode to the original hidden state space. So because of this regularization, we commonly use some kind of L1 sparsity regularization with the hyperparameter lambda. So because of that, we cannot perfectly achieve the zero reconstruction error. So this may shift the distribution of the hidden vector in the internal LLM state. And we showed the performance degradation in the later table. So because of that, we cannot directly applying the manipulation through SAE. So although I know that sparse autoencoder is not designed and considered for manipulations, but maybe you may see some kind of these manipulations like steering or some loaded clamping. But this is also their behavior is interesting, but cannot be applied directly because the original LLM's performance is dropped. Actually, they show worse performance. So let's think about the safety alignment. So if we found some unsafe features in features by SAE and we want to clamp this to 0 or negative, but by just simply applying the SAE occurs the performance drop in benchmark scores and maybe other. There should be some other cases. But anyway, so because of this, we cannot directly using in a real world and in practice. And the last one is some kind of different thing, but you may agree that SAE is pretty heavy and expensive because the number of features are the large number of features requires the full matrix for encoder and decoder weight matrices. So this is also computationally expensive, heavy, and also they require some many parameter and disk space. So all of these are limitations because the 1, 2, 3 is from the postdoc training, and the last one is some kind of decomposition. can be resolved by decomposition. So this is our introduction, and okay, and the case of mixture of experts. This is quite simple. We use this. Also, we wrote some limitation of the MOE in this section, but actually this is simple. Many MOE models use quite a small number of experts. The maximum number of experts were 1,024, and so because of that, we think that we need to increase the number of experts like SAEs so that we want to see the limit, see what will be happened in MOE, and we want to verify that if MOE will act like SAE. So this is our point. So this is let's move on to the method part. So sparse mixture of expert. This is preliminary, and the formulation is quite simple. This is expert network, and we aggregate the output of each expert output by multiplying the gate probability, their corresponding gate probability. So this is the basic sparse mixture of experts, and I want to introduce another previous work, peer. So actually, I mentioned that the maximum number of experts I tried was 1,024, but actually there is another case. Peer is actually from DeepMind, and they increased the number of experts to a million scale with the parameter efficient experts. This is really small number of parameters. So actually, you can see in this this bottleneck, the number of hidden neuron is just a single neuron. So actually, this is not a matrix but a vector. Anyway, so this means that we need to prepare really small experts because the number of experts is million scale. So they are talking that they're saying that the mixture of expert requires two steps. The first one is to retrieve the corresponding experts, and then the second one is to collect the corresponding experts and then pass to these experts. So actually retrieving is a sparse operation, and this is not actually these operations do not occur any computational cost because there is no any multiplications or matrix multiplications or some additions or subtractions, or there's nothing. But they said that the actual problem is in stage 1. To find the proper expert, they need to compute the gating score, and actually this is the some kind of coefficient to each expert. But the number of experts is million scale, so we have to compute a million gating scores. So this is quite computationally heavy. So they use the product key methods, and this is actually from the PKM, the product key memory, and this is some kind of clustering, k-means clustering. Like, so actually do not use any k-means clustering, but the idea is from k-means like hierarchical retrieving. So some kind of building a tree to make a subcluster in each retrieving. So maybe I will explain it later. So as you can see, this is also in the paper. So first one, we retrieve among the square root of n experts, not full n experts, and then find the sub-expert groups, and then make a Cartesian product to find the full retrieve from full expert pool. So using this, they can effectively reduce the gate probability calculation cost, but they still requires full million of experts. So not in this paper, but we wrote about this. So you can see in this sentence, so building 1.3 billion activate parameter LLMs requires 103 additional billion parameters to storing these billion experts. So this is really impossible in practice. We want to reproduce the peer, but we faced the memory limitations. And in addition, gathering the experts sparsely, and this is performed token-wise, so that the gradient buffer is really large, so we cannot actually do the backpropagation and computing the gradients of each expert. This is almost impossible. Really require multiple times of the gradient buffer. So we developed another decomposition methods for experts. So you can see in this diagram, the peer decompose the routing probability to two distinct groups. So instead of calculating full n routing scores, they compute the square root of n distinct routing scores, and then combine them and find the corresponding expert from the model. But they still need full number of experts. So like product key, we divide the expert weight into two distinct groups. Like experts is usually experts consist of two linear layers, so we can divide into top and bottom layers, and then we can also split into left sub MLP and the right sub MLP to combine them, and they can be combined into a single expert. So the idea is quite simple. Like this is like peer to find the subgroup corresponding expert indices, and then using this information, we find the corresponding left and right. Maybe it can be the top and bottom layers, but find the proper weights. And this is actually the weight of the network. So this is the linear layer, and this is the linear layer, and the weight is constructed by just combining the left one and the right one in every token. So combining and making this expert, and then we will pass the vector, the input vector to these experts. So why do we do this? This can reduce the memory usage, and also in this paper, you can see this is the definition of the Monet, and making these to be dense routing, replacing to the dense routing vector, then we can actually reordering the summation operation like this. So we need to make this perform as Hij, but we can reorder so that first one we can compute this, and then we can reuse the result of this tensor output to compute this, and then after computing this, we can reuse this to compute the final output. Like this, we can effectively reduce the memory usage and the computational cost, and of course the gradient buffer and backpropagation, we can reduce this. So we made two different kind of decomposition. First one is horizontal, and the second one is vertical. So actually, horizontal decomposition is really natural idea. Maybe many people can imagine about this, but actually, the training performance is not really good. You can see this is orange, and blue is the original model's training loss curve, and the purple is, as you can see, the horizontal decomposition loss curve. But this is not really good as the original Llama's model. So we quickly developed another method, vertical decomposition, and then we can finally achieve almost similar to the dense llama model. So for fair comparison, we trained the dense llama, the original decoder model, and the Monet horizontal and the Monet vertical decomposition method in 100 billion tokens fine web edu corpus. And then we also trained the Vision Monet. This is followed by the lava method. So we just simply align the vision encoder's hidden vector, hidden representation space to the LLM's internal space. So this is for the qualitative analysis. So let's move on to the results. So this paper is actually kind of architecture paper. So we have to demonstrate that our model is not really is competitive to the original Llama's model. So we evaluated on 8 LLM benchmark dataset, and we compared many parameter size and in 0 shot and 5 shot. So as you can see, the horizontal decomposition achieves some not really competitive, but we quickly developed the vertical decomposition, and we can finally achieve better than horizontal decomposition. And we also included the OLMOE, some kind of baseline, and we also included the GEMMA's benchmark score with applying the sparse autoencoder in a single layer. So we applied the middle layer's sparse autoencoder without any other manipulation. So you can see, just applying the sparse autoencoder without any other manipulations, and the SAE's reconstruction error leads this benchmark scores dropped. So just a single layer. So this is for our, as I mentioned in the previous slide. This means that using sparse autoencoder is not proper to applying for the manipulation in the real world and in practice. So this is, maybe there should be better approach to recover this reconstruction error, but this is really naive and theoretical approaches to show this. So also we prepared the qualitative results like SAE. So I mentioned that we are thinking that MOE, the large number of experts with a large number of experts can be performed like sparse autoencoders. So we prepared sparse autoencoder like feature visualization, actually. So this means that these tokens are routed to these experts, and these tokens are routed to these experts. So this is chemical compounds, and this is the US state-related tokens. So they are activated, and actually activated means that they are routed with large probability, large coefficient to these experts. So you can see this example. And this is another example, but we think that this is pretty important because Bay Areas and Bayesian, they use same Bay tokens, but according to the context, this Bayesian, so this LLM is autoregressive, so they cannot see the Bayesian, the later token. So according to the previous context, they think that Bay is related to the Bayesian, the mathematical or statistics things. So these tokens are routed to these experts. And this is Bay areas. The Bay tokens, if this is some kind of Bay areas of water like related, then these Bay tokens are routed to this expert. So they are also the same token, but they show different semantics. So the different semantic experts are observed. So this is some kind of examples, and we also included the multimodal examples, as mentioned in the vision Monet part. So this is actually, honestly, obvious things because lava is to align the embeddings to the imaging vision encoders embedding space to the LLM's vocabulary space. So this should be interpreted as really natural and obvious things. But as you can see, the green images and green tokens are routed samely, and this purple is the same. And this is aviation, so miles or some kind of flying, and these semantics are also collected with these airplane and sky images. And this is also water related, river, ocean, and water. And so you can see in this example, not only for the tokens, but also the semantically similar tokens are also can be gathered together. So this is some kind of abstract expert. So we prepared these qualitative examples of expert routing. So we also do some quantitative analysis to demonstrate that increasing the number of experts can achieve like SAE, like monosemanticity. So this was actually our main problem, that we cannot actually demonstrate and prove that our model had high monosemanticity in monosemanticity restrictedly. So we want to show in indirect ways. So this is MMLU score benchmark, and we organize the MMLU examples by these 14 taxonomy, and this is actually from MMLU Pro. So we collected, we gathered the samples, and then we also identified which expert is related to which category, and then this means that for the case of business, we actually remove the business-related experts from the model and then evaluate the MMLU scores. So you can see the business is highly dropped it, and then other models are quite the same as the original score. this looks like diagonal matrix, but Gemascope they show significant performance drop. So this is actually contrary to this main table. These Gemma 2's cases, we applied SAEs in every layers to remove this. This is because if we remove some concept from the single SAE, the related knowledge can be recalled after recalled from the after layers can be recalled. So we thought that this to remove restrictly, we have to apply SAE in every layers. So this is ambiguous result. So we also compared with other baselines, so OLMOE and Llama. So for case of Llama, you may know about Rome or Mammoth. They treat the MLP layers, first one as key store and the second layer in the MLP is as the value store. So the intermediate activation is some kind of can be treated as the key coefficient of the concept. So like Rome, we treat this as the routing probability, but this is ambiguous. And OLMOE is actually same as our Monet experiment settings, but this shows that small number of experts cannot actually achieve the monosemanticity. So removing engineering related experts can be affected to other categories. This means that the knowledge is spread across the experts, not just separated and isolated correctly. So, okay. And this is kind of toxicity. So this we use the correlations to identify which expert is actually toxic and contains the toxic knowledge. So this means that these experts, in case of this expert, the large expert activation occurs large toxicity scores, and actually the sentences toxicity score is high when the expert routing score is high. So you can see the sensor tokens also contained and the dam tokens we found. So using these correlations and using the threshold. So this is the completion example. So we use the real toxicity prompt. So the more the more we remove the experts, the quality is increased. And yes, so you can see these examples also in this appendix. This section, so you can see this. So this means that we can also find some toxic experts in MOE models if we increase the number of experts. So also we do some quantitative benchmark scores. So the first one is real toxicity prompts with Perspective API, and the second one is Toxigen with their Roberta score. So as you can see, more masking, we can achieve better toxicity, lower toxicity score with almost preserving the LLM performance. So this is average performance is same as these tables average score of 8 among 8 benchmark scores. So yep, and this is this is the analysis about toxicity, and also we tried the code generation. So we also trained the code Monet to generate the code, and for these 6 languages, we masked the Python-related experts. Then the score of Python. This is like human evil dataset. So the model should create the solution about the problem, but after removing the language experts, it cannot generate the related code. But other languages' score is almost preserving. So you can see the summarized score like this. So we also do some monosemanticity demonstration on the code generation cases. And finally, we do some self-explaining SAE using like selfie and patch scope variants by just gathering the routed tokens embeddings and average them and pass to the patch scope like prompt so that we can get these descriptions. So instead of using some external LLMs like GPT-4o to request to make a descriptions, we can use this alternative method to create the descriptions by the model itself. So this is example. So okay, so the things that prepared in this slide is and so I think I handled almost everything in the paper. So this is another example of the code generation. So you can see after removing the Python related experts, they can not generate the Python codes, but they are just creating the bash script and the C code instead of just writing. This is really simple, return lengths of strings, but they cannot do that. The model cannot do, but just creating the C code, and this is not work properly. So, okay, so that's what I want to say. Well, that's what I want to show. So I think I enoughly showing the contents of our paper. So this is a frequently asked question, but maybe it would be better to directly listen from you instead of reading this, if you have. So, okay, I will finish my presentation, and thanks to listen my presentation of our paper. And if you have any questions, then feel free to ask about this. Thank you.
All right, thank you, Jungwoo, for a great presentation. Can I ask a question? Hello, can people hear me?
Yes, we can hear you.
Okay, yeah. So, I think that the Monet architecture is very interesting, and essentially, like what I see is 2 main innovations to allow it to scale to this large number of experts is you have like 2 routers instead of 1, and then the decomposition of experts is essentially parameter sharing. It means that like expert ij shares like half its parameters with expert ij prime. So I was wondering if you looked into like the relation between experts that share parameters, like the Bayesianism agent, right? So let's say Bayesian agent is agent ij, right? So what does agent ij prime do, right? Like he's half Bayesian, half like some other thing. Like what? Yeah, it's just interesting to try to understand how the relationship between these different agents or different different experts.
So you're asking the effect of sharing the parameters between the different combinations, or like, what? Can you repeat the question?
Yeah, exactly, right. So each expert is a combination of, in the vertical decomposition, of a left half and a right half. So like if you have the Bayesianism agent, for example, right, it's a specific left half with a specific right half. So like how does that, have you investigated how agents that share that same left half but have a different right half, like are they just like completely unrelated, or are they related, like instead of Bayesianism it's a frequentism agent, or something like that?
Okay, so just like you mentioned, each of the experts in our model is a combination. So it is decomposed into two different weight groups, whether it is horizontal or vertical. We try to investigate through the co-activation of the weights of the factorized weights. But as you can see, there are like 512 times 512 weight groups, which results in 262K number of experts. It's kind of different. It's kind of difficult to track all those 262K number of experts co-activations, and just like you said, some do kind of Bayesian analysis. So instead, we probed into the activation ratio of the experts. So we need to see whether only the portion of experts are being used, or are we observing only are there any dead experts in the weight groups and so on. So we kind of naively approached or alternatively approached to see whether only few number of experts are being used or not. And we observed like more than 90% of our experts, or 90% of our combination have been used for the C4 validation set. So I think it was okay for us to conclude that the combination of experts has been diversely used throughout this C4 validation. At least that's what we found. Is that gonna kind of like satisfy your inquiry?
I mean, it's not exactly what I was asking. So, um, like in your table, in your figure two, you have expert number 54,136 is the Bayesianism expert. So what I'm asking is, like, that expert has a specific left half and a specific right half. So you could like do the auto interp technique that you use to find that this expert 4,136, right? You found this is a Bayesianism expert using auto interp. So what if you did auto interp on other experts that have the same left um, half expert as this expert, but a different right half expert, and just see what are these experts, and then experts that share the same right half expert but have a different left half expert, right? And like, I mean, I'd be interested in knowing, like, how do these relate to this Bayesianism expert, right? Are they of related concepts because they share this half expert, or are they just like unrelated?
Yeah, I think that's a good suggestion. But the thing that I just explained is kind of related to your inquiry, because like if the half of the weight if half of the experts has been semantically meaningful, and if it's used repeatedly, then we will not be able to observe the activation ratio of C4 validation set. I mean, if the portion of the expert has been used to the similar concepts, then it'll be, of course, impossible to cover the entire web corpus that we feed forward through. So I think that's a good suggestion. I think we need to look into that. Jungwoo, do you have anything else to say about it?
Then how about wait a second, please. So how about just calculate the index of the Bay experts left and right index about Bay areas and Bayesian. Let's wait a second, please. So you can simply divide the index of experts by 512. So wait a second, please. So how can I? How about using the? Where is the chat? How can I type this? So
I think you can type it here.
where's the complete?
The top right.
그 어디다 채를 해야 돼? This one. Okay, so
Right over here.
for the this is the index. So okay, where's the to it's the areas and a 예 얼마니 105에 7이요. So as you can see, the left and right is not equal. Any part of index is equal.
Mm.
Yeah, so this is what I want to say.
But definitely your suggestion is pretty valid because even though we show that the diverse number of experts has been used throughout covering the web corpus, it's kind of worth taking a look at how the weight groups has been used to constitute the concept. Like if the weight index I has been used to with other combinations, is that going to result in different semantic concept? And I think it's kind of worth looking at. So thank you for your suggestion.
Hey, you're welcome. And one more quick question is, I'm not exactly sure how one will do this, but have you done like an exhaustive search? Like this figure here on screen is very impressive, but like I don't know if these are just if all of them are this impressive or these are just the ones that were the most impressive, you know what I mean?
Oh, you're talking about the cherry picking?
I don't
Oh,
mean to
like-
accuse you of cherry picking. I just want to know if there's like if you did a more like an extensive analysis or just like looked at certain ones.
Okay, so thank you for mentioning. We actually have a viewer for the experts. Share through the chat. So yeah, you can actually look it up. But as you just mentioned, not all the experts are fully human interpretable. Of course, you can anticipate that, but I would say reasonable amount, especially when it goes to the when it goes close to the language modeling head. For example, like the group notated on the figure means that the earlier groups are closing to the embeddings and the later groups are closing to the language modeling head. And as you can anticipate, the earlier groups are more close to the entity concepts. Like it looks at the one specific tokens, and it's kind of difficult to comprehend what it means. But of course, there are some difficult, but as you go to the later groups, I think it was pretty okay for us to what this expert has been functioning to constitute the concept, to constitute the semantic concept. So yeah, just look at the viewer.
Yeah, cool. Thank you very much.
I have a quick question about like the fact that the routing is like on a high level, it is kind of controlled, but what kind of concepts gets divided into what? That part is a bit unsupervised, right? So it's a bit like SAEs where once you train SAE slash Monet in the technical detail that you guys explained, with the clusters that you get or the experts you get are like highly interpretable, but you don't know what you're gonna get until you do it, right? So and then you kind of postdoc use some kind of auto interp technique and see how which experts light up for which input. So the analysis method would be pretty similar. Is that an accurate?
Could you
Um,
repeat the question? Like, so you're asking like, since this expert decomposition and expert composition method is unsupervised throughout the pre-training,
mhm.
and what was the next thing that you said?
I was curious whether the same sort of auto interp technique could be applied because what we get is like we don't know what we're gonna get beforehand. So it's useful for like finding interesting features that you wouldn't have expected, something that's out of distribution or something you didn't necessarily explicitly route. Were there any of those cases where you found such things?
Just like you mentioned, it's pretty similar. As explained by Jungwoo, the self-explained experts is just a replication of the other method in the selfie and other papers. I'm not so sure about like not so expected results from the analysis. What should I
Like a
say?
cluster that you wouldn't have
Oh,
expected to exist.
Sorry, but are you asking about identifying the category-related experts?
Yes.
Oh,
Category
okay.
related experts that you didn't explicitly route, but it ended up being interesting or interpretable in a meaningful way.
So also I included that contents in the appendix. So as I presented in the slide, this correlation toxicity is a kind of identifying the toxicity, toxic experts, and also 여기 안 적어놨나 우리가?
어떤
Do you remember, 영진아?
about what? Like categorical expert?
Yes, identifying the domain specialized experts.
Domain specific experts. Oh no, we have it in the like very end of the appendix. Like very end, like last page.
Last page.
Yes, like last 3 pages or so.
Last page?
I think you're meaning like the psychology and the business experts,
This
right?
is toxic expert identification.
Okay, now I have another question. So, how do you index into a specific concept you want to target, erase, or steer towards, or whatever, without the concept-specific expert?
Concept specific expert. So can you say that again?
Yeah. If you want to prune, let's say, information about engineering, you would find a set of experts that are related to this, right?
Yeah.
Based on the
Definitely.
pro interp technique you guys use, and then you turn them off during the forward pass, and that would effectively prune those concepts, and it wouldn't like represent in the output. If you don't have concept specific experts, how would you go about it? How did you guys do it?
I see. So you're asking like since the concept specific experts isn't supervised during the pre-training, like how do you detect the concept specific experts after the pre-training and so on? Okay. So we used MMLU Pro benchmark, which is a basically human labeled evaluation set, and they have about 14 categories like business, psychology, engineering, and economics, and so on. So we look at the. Go on. Can
I see.
Yeah. So and after categorization through the benchmark, we feed forward through the benchmark. Like and collect the routing statistics. Like, are there any experts that shows distinctive routing probability to a certain category? For example, like if there are expert indices that are activated to the economics, whether in the same time, meanwhile, they're not activated to the history categories and so on. So we collect those like expert specific statistics, and we use it in a very simple approach. We just measure measure the probability of ratio of 2 to 1. So, for example, if the expert IJ is activated to the history category, the double amount of the other categories, then we define it as a specialized expert, and then we just collect the information, we mask it, and the feed forward through it, and collect the statistics. Yeah, so that's how we did it. Pretty simple.
Thanks so much for the clarification. Also, one quick question as to like because although like the training cost isn't that great and it's very like competitive with other models training, have you also thought about maybe turning an existing transformer into a Monet style model by doing some sort of like clustering? And that would, yeah, recycling models using this decomposition methods plus like key value clustering methods. So first make it into a mixture of experts and then apply the decomposition to make it into a full Monet. You don't even have to like retrain it. That would like significantly lower the training costs or fine tuning costs.
Yeah, that's actually a good proposition. But the thing is, it's kind of difficult because we need to have a learned route. So this is based on learned router through the pre-training, right? So decomposing the polysemantic MLP into experts and then connecting to the router is, I think, it's kind of difficult for now, and we haven't looked at that part yet. But I think it's pretty interesting.
There's a paper that does the first part. I don't know how to do the second part, but I know there's a first part of it. They like take an existing transformer, make it into an MOE, and maybe it is as clean as doing it from scratch.
I think it's pretty okay for transforming existing dense model into an MOE model, at least for now. But the thing is, like, the oil MOE that we mentioned, it has 64 experts, which is a pretty large amount of experts that we have observed by the time we write the paper. Like, for example, DeepSeek MOE uses 256, and there are other models that uses more. But the thing is, like, we looked into the 64 experts large language model, which it was like 7 billion parameter model, but we didn't. Unlike the paper's original claim, it was kind of difficult to observe the specialization of the experts. Like, we said, we determined this specialization based on the routing probability of ratio of 2 to 1, right? So one expert is specific to history, whether it is not activated to law, and so on. But in case of oil MOE, that kind of specialization was not observable. Like, the route probability is pretty much about the same and evenly distributed. Like, so I think this is because of the training scheme. Like, we didn't use the expert parallelism, whereas the other MOE models use expert parallelism, which kind of reduces the specialization of the experts. That is mentioned in the other paper, like Quen paper. So, yeah, it is possible to map the current dense models into existing MOE models, which we believe is kind of polysemantic in the essence. But we believe our Monet is more specialized compared to other existing MOE models because we have a substantially large amount of experts, and also we do not use the expert parallelism. So I think it's kind of difficult to convert the polysemantic dense models into monosemantic R model. At least that's my personal opinion, though.
All right. Thank you so much.
Any other questions? We're very open to suggestions because we're working on version 2 and so on.
Will you just make it bigger and like more diverse data sets?
Oh, make it bigger.
Yeah, I don't know, like bigger or just do more interventions, more specific interventions, and see how. well we can index them?
Yeah, I think that's a good beginning. Like our large language models are trained on 100 billion tokens, whereas like Jungwoo recently did another research, and he trained on 1 trillion tokens. So maybe we can do that.
Cool.
Okay, if there are not so many questions available, like, is there anything else left to say, Jungwoo, as a closing remark?
대신해주세요.
Okay. So thank you for all coming, and then we have email attached to the original paper. So if you have any inquiries, ask Jungwoo or me. The paper is based on Jungwoo's idea while we were eating lunch in the last June. So if you want to ask about the philosophy and the idea, and also the engineering is mostly done by Jungwoo. So if you want to ask the engineering details, you can ask him, and also you can ask me about it. And thank you for the invitation. And you can email us or just direct message us through the Discord if you have any questions. And thank you for inviting us. Thank you.
Thank you for coming. I guess I'll stop the recording now if no one else. I'll wait a bit in case someone else wants to ask more questions, but otherwise I'll just stop it.
Yeah, you can ask questions now, but if we have time. So. Yeah, you can just ask us through the personal message. So yeah, it's gonna be fine. Yeah, thank you.
Yeah,
Thank
I guess
you.
I'll just stop the recording because it doesn't seem anyone else is saying anything.